I have to admit, looking at this massive stack of research we pulled together for today, I'm actually feeling a little cold.
Oh, yeah.
Yeah, and it's not just the office AC. We are looking at machines that operate at temperatures that, frankly, just shouldn't exist in nature.
It is spooky territory, for sure. Because we usually talk about technology heating up, right? Overheating phones, server farms needing these massive air conditioners. But today, we're looking at the absolute other end of the thermometer.
Exactly. We're talking about the quantum revolution. But not the part that makes the splashy headlines. We aren't here to talk about breaking encryption codes or the magical processing speed that everyone hypes up.
Right, the sci-fi stuff.
Exactly. We are here to talk about the elephant in the room,
The bill.
the energy bill, which is honestly the one thing that might actually kill this entire revolution before it really gets off the ground.
So for this deep dive, we've got a really interesting mix of sources. We are pulling from deep technical breakdowns of power demands, some recent sustainability reports, and architectural comparisons across the industry. And our mission today is pretty clear. We need to look past the quantum supremacy hype and figure out the physical reality of these machines.
Right, because we need to know if the energy cost of quantum computing is a fatal flaw or just a growing pain. It's this thing the sources call the energy efficiency paradox.
Which is fascinating because on paper, quantum computers should theoretically be the most energy-efficient devices we've ever built. I mean, physics says they should just sip power.
But the reality we found in the reports is that they drink it like a fire hose. So let's get into the why. And I want to skip the basic, this is a qubit 101 stuff.
Good call.
Yeah, if you were listening to this deep dive, you already know a bit is a 0 or a 1, and a qubit uses superposition and entanglement to be both. You know about the exponential scaling, how just 10 qubits can handle over 1,000 calculations at once.
Right. The raw power is established.
So what I want to understand is the fragility problem, because that seems to be the core of the energy issue.
That is exactly the right place to start. The fragility is the root cause of the whole massive energy bill. Because in a classical computer, a bit is a very robust thing.
You need a decent little jolt of electricity to flip a 0 to a 1.
Right. It's stable.
You can shake your laptop, you can leave it in a hot car, and your spreadsheet doesn't just spontaneously disappear.
Exactly. But a quantum state, it's like balancing a pencil on its incredibly sharp tip in the middle of a hurricane.
And the hurricane is the environment.
Yes. Specifically thermal fluctuations, vibrations, electromagnetic waves, anything that causes what we call decoherence.
Decoherence, that's when the data gets destroyed.
Right, because temperature is basically just atoms jiggling around. If an atom in the chip jiggles and bumps into your qubit, or even just radiates a tiny bit of heat energy nearby, that delicate quantum state collapses entirely. The calculation just vanishes.
So to stop that jiggle, you have to freeze everything.
You have to freeze it to an extreme degree.
And we aren't talking about a kitchen freezer here. The standard for superconducting qubits, which is the architecture that giants like IBM and Google are largely betting on right now, is around 15 millikelvin.
That's 0.015 Kelvin.
Right. And I was trying to find a comparison for this in our notes because that number is hard to wrap your head around. Deep space, literally the empty void between galaxies, is about 2.7 Kelvin.
So these machines are running more than 100 times colder than the dead of space.
It's wild. It is arguably the coldest place in the entire universe, created right here on Earth, inside a lab.
And that requires some serious heavy lifting. You obviously can't just use a fan or a standard compressor for that.
Which brings us to the dilution refrigerator.
The golden chandelier.
Yeah, in the photos, it looks like this massive steampunk art installation, all these tiered gold plates and wires. But the physics inside is what really caught my eye in the research.
Right.
It's not just pushing cold air around, it mixes isotopes.
It's a really brilliant application of thermodynamics. You use two specific isotopes of helium, helium-3 and helium-4. When you get them cold enough, they actually separate into two distinct phases.
Sort of like oil and vinegar.
Exactly like that, but with quantum fluids.
And the cooling happens right at the boundary where those two liquids meet.
Precisely. To move atoms from the helium-3 rich phase into the helium-4 rich phase requires energy. It's an endothermic process, meaning it literally sucks heat out of the surroundings to fuel that phase transition.
So it's using entropy to force the temperature down.
Yes. It's forcing order into chaos, and the tax for doing that is heat absorption. But here's the catch. Pumping those isotopes around, compressing them up at room temperature to get the whole cycle going, that takes massive mechanical power.
I saw the specs for Colossus in the reports. That's the world's largest dilution fridge developed at Fermilab. The thing is an absolute beast.
It really is.
And the power draw for a typical setup of this kind is generally between 25 and 50 kilowatts.
And that is just for a single machine.
Let's contextualize that for the listener. 50 kilowatts running 247 is roughly 600 kilowatt hours a day. An average household uses maybe 20 or 30 kilowatt hours a day. So one quantum computer just sitting there idling is consuming the annual energy of 20 to 40 average homes.
And this highlights the massive shift in the paradigm. In a classical data center, cooling makes up maybe 2 to 20% of the energy budget. In quantum, cooling is the vast majority of the energy.
Which brings us to the paradox, because where is all that power actually going? It's not going into the math.
No, it's not. This is the core of the energy efficiency paradox. The actual quantum processor, the physical qubits doing the calculations, consumes almost negligible power. We're talking milliwatts.
That part made me stop and reread the report. A few milliwatts for the actual brain of the machine.
It's practically zero. Because superconducting circuits have zero electrical resistance, the electrons flow without losing energy as heat. The computation itself is essentially free from a thermodynamic perspective.
So we have a milliwatt brain living inside a megawatt life support suit.
That is the perfect analogy. You are spending almost your entire energy budget just to create the infrastructure to keep the qubits alive.
The cooling stages, the massive pumps.
And the control electronics. For instance, IBM's Eagle chip needs about 10 kilowatts just for the control and readout electronics.
Plus the cryogenic amplifiers.
Right, because the signals coming back from the qubits are so incredibly weak, you need amplifiers to boost them. But traditional amplifiers generate heat.
Which forces the fridge to work even harder to remove that heat. It's a vicious cycle.
It is. But the takeaway here is actually optimistic. Because the calculation itself is so efficient, if we can just fix the cooling efficiency, quantum computers could theoretically become vastly more efficient than classical ones.
Okay, but do we have to fix the fridge, or can we just ditch the fridge entirely? Because one of the sources explicitly states that superconducting isn't the only architecture out there.
Oh, absolutely. Not all quantum computers are frozen. Superconducting is just one camp.
Right. There's a rival camp that seems to be screaming that they don't need these extreme temperatures, the neutral atom of computers.
Yes, companies like Pascual are leading this charge. They are the highly efficient rival.
They use lasers instead of superconducting circuits.
Exactly. They use what are called optical tweezers. These are highly focused beams of laser light used to trap and hold individual atoms in a vacuum chamber.
And the energy difference is stark. The sustainability report noted that a typical neutral atom setup pulls somewhere around 2.6 to 7 kilowatts total.
Right. Compared to the 50 kilowatts for the superconductors, it's about a tenth of the power.
Because they don't need to reach near absolute zero. The atoms themselves are cold, but they are cooled by the lasers, not a giant dilution refrigerator.
Exactly. Then you also have trapped ion computers, which sit sort of in the middle. They use electromagnetic fields to trap ions. They have incredibly high fidelity but moderate power needs.
But the real prize, what the sources call the Holy Grail, is room temperature quantum computing.
Yes. If we can achieve that, everything changes.
Photonic quantum computing is one approach for this, using particles of light, photons, to run the calculations.
Because photons don't interact with the environment the way delicate atoms do. They have the potential for true room temperature operation.
There's also topological quantum computing, which is theoretical but could use exotic materials to work at ambient conditions. And we have to mention that recent 2025 Stanford University research.
So that was a massive breakthrough.
Right. They developed a device using a thin layer of molybdenum diselenide that actually operates at ambient conditions.
Which is huge. It proves the concept is physically possible without the massive refrigeration tax.
Okay, so let's pivot to some myth-busting here. Because if we are going to look closely at the energy bill, we have to be realistic about what we are actually buying with that energy. And the term that gets thrown around a lot is quantum supremacy.
I really dislike that term. It's very misleading.
It sounds like a sci-fi movie villain.
It does, and it implies that the quantum computer is simply better at everything. Like it has completely defeated the classical computer.
Which is a huge misconception.
Exactly. When a company like Google back in 2019 with their Sycamore processor claims supremacy, they just mean the computer did one specific, highly tailored task faster than a classical machine could.
The more accurate term should be quantum advantage.
Right. Because classical computers, like the Frontier supercomputer, are still incredibly powerful and far better at general tasks. You wouldn't use a quantum computer to run a spreadsheet.
Another myth that drives me crazy is the infinite parallelism idea.
Oh, the idea that a quantum computer just tries every possible password combination at the exact same time.
Right. People think it just brute forces everything instantly.
But that's not how it works at all. It uses wave interference patterns to find the correct answer. You have to design the algorithm so the wrong answers destructively interfere and cancel each other out, while the right answer constructively amplifies.
And because it's quantum, it's probabilistic. It requires multiple runs to get statistical confidence in the answer.
Exactly. You don't just ask it once and get a definitive yes or no. You run it many times to build certainty.
There's one more myth to bust, the idea that more qubits equals a linearly higher power bill.
Right. People assume if you double the qubits, you double the megawatts.
But the sources clarify it's not linear. The massive dilution refrigerator is a fixed cost. Once it's running, adding more qubits doesn't double the power it draws.
However, scaling does introduce a different problem. Adding qubits adds heat via the control cables and the amplifiers.
Which perfectly transitions us into the hardware fixes the industry is working on. Because the engineers aren't just ignoring this problem, they are actively trying to stop the heat leaks.
Right, starting with what's called the cable problem.
This felt so low-tech to me. To control a qubit, you have to run a physical coaxial cable from the warm outside world all the way down into the freezing core.
And as you add more qubits, you add more cables.
Yeah.
Each cable is basically a tiny little copper highway conducting heat straight into the most sensitive part of the fridge.
So what's the solution?
One approach is in-fridge controllers. The University of Chicago is doing some fascinating research on putting the control electronics inside the cold zone.
So you generate the control signals locally in the cold, bypassing the need for those long cables coming from room temperature.
Exactly. You stop the heat leak at the source, but then you have the challenge of making sure those in-fridge controllers don't generate too much heat themselves.
And speaking of generating heat, we have to talk about the amplifiers. There's a startup mentioned in the reports called Quebec.
Yes, Quebec is doing really vital work here. We mentioned earlier that the standard cryogenic amplifiers boost the weak quantum signals, but generate a lot of heat in the process.
Right, which fights the fridge.
So, Quebec developed what's called a zero-heat amplifier, specifically a traveling wave parametric amplifier.
Which cuts heat emissions by an unbelievable amount. The report said 10,000 times less heat than current industry standards.
It's a game changer. If they can launch that successfully, and they're aiming for 2026, it dramatically reduces the cooling burden.
Then there's the microfluidics approach.
Right, from UC Santa Barbara.
Instead of cooling a massive chamber, they're developing on-chip cooling, running super chilled fluids directly to the specific hotspots on the chip.
So you wouldn't necessarily need a warehouse-sized fridge for future systems. You get much more targeted, efficient cooling.
Okay, so with all these fixes in the pipeline, we need to ask the big so what question. From a sustainability standpoint, what is the net impact of this technology?
We have to look at the environmental costs first. Manufacturing these incredibly precise machines requires rare materials.
Like the helium-3 we talked about for the fridge, that's extremely scarce.
Very scarce. And then you have the massive water usage required to cool the classical data centers that support the quantum hardware.
But the sources also present a strong counterargument, the net positive argument.
Yes, the argument is that the energy we spend running the quantum computer will be offset by the incredible things the computer invents.
Let's break down some examples from the reports, starting with the energy grid.
Our current energy grids waste terawatts of power simply because routing electricity efficiently across a massive network is an incredibly complex optimization problem. Classical supercomputers struggle with it.
But a quantum computer could theoretically optimize grid flows in real time, saving far more energy than it consumes.
Exactly. Or discovering new, highly efficient materials for next-generation batteries, or vastly improved solar panels.
The example that really stuck with me was fertilizer production.
Ah, yes. The Haber-Bosch process.
Right. We use it to make ammonia for fertilizer, and it's heavily reliant on natural gas. It's a brute force process that consumes extreme heat and pressure.
It actually accounts for a massive chunk of global energy use and emissions.
But a quantum computer could simulate biological enzymes that do the exact same thing at room temperature.
Nitrogenase. Nature does it effortlessly, but it's too complex for classical computers to simulate accurately. A quantum machine could model it, leading to a new catalyst that slashes global emissions.
So when you compare the energy use, a classical supercomputer like Frontier uses megawatts of power to brute force a problem, while a quantum machine might only use kilowatts to solve that specific problem natively.
Right. For those very specific, highly complex problems, quantum is actually the low-energy solution.
Which leads us to what the architectural breakdowns call the hybrid future. We aren't going to just throw our classical computers in the trash,
Definitely not. The future is hybrid data centers.
like the one IBM is setting up in Europe.
Exactly. You will have classical machines and quantum machines working together in the same facility. The classical computer handles the standard data processing, the web hosting, the easy stuff.
And when it hits a massively complex optimization or chemistry problem, it hands that specific task over to the quantum processor.
The quantum machine acts as a specialized accelerator. Each machine does what it's best at.
So we are currently in this transitional period. The machines are inefficient, they're power hungry, and they require absolute zero temperatures.
They are definitely in their awkward growing phase.
But it raises a really provocative thought. If a 25 kilowatt quantum machine successfully models a new carbon capture material that helps stabilize the climate, does the electric bill to run that machine actually matter?
In the grand scheme of things, no. The value of the solution far outweighs the energy cost of the calculation.
It really challenges how we think about efficiency. We can't just look at the power going in, we have to look at the value coming out.
That's the only way to accurately measure it.
And looking at all this, it makes me wonder if our entire concept of energy consumption is just a relic of the classical computing era.
How do you mean?
Well, right now we think of energy as something we burn to crunch numbers. But in the quantum era, energy is almost like a currency we spend to actively lower the entropy of a tiny localized space. We are buying a pocket of perfect stillness. So maybe the ultimate measure of a future civilization won't be how much total energy it can harness, but how much localized order it can purchase with that energy to run the fabric of reality itself.
That's a profound way to look at it. We are trading crude power for profound order.
Exactly. Well, we'll leave you with that thought to mull over. Thank you for joining us on this deep dive into the freezing, power-hunky paradox of quantum computing. We'll be back next time with another stack of reports to unpack.